When installing an interruptible air conditioner circuit, a grounding electrode conductor, or GEC, should be installed to the cold water pipe. The grounding electrode conductor provides a path for fault currents to flow back to the source. This protects personnel and equipment. For a two-circuit panel dedicated to a dryer or stove, it is generally not required to install a grounding electrode. However, it is recommended to verify with local building codes and regulations, as they may vary from the National Electrical Code. In a dual-service installation, such as in a two-family home, it is required to install grounding electrodes for both main panels. This is because each main panel must independently establish a low-impedance path to ground. The purpose of a grounding electrode is to provide a low-impedance path for fault currents to flow back to the source. This helps to ensure that electrical faults do not pose a hazard to personnel or damage equipment. In the case of an interruptible air conditioner circuit, the grounding electrode conductor is essential for the safe operation of the circuit. Without a proper grounding electrode conductor, fault currents could flow through unintended paths, causing fires or other hazards. While it may not be explicitly required for a dedicated dryer or stove panel, installing a grounding electrode is still recommended as a precautionary measure. It provides an additional level of protection in the event of a fault. Grounding electrode systems and the National Electrical Code serve to ensure electrical safety by providing a path for fault currents. This path guides the current back to the source, tripping a circuit breaker or fuse and interrupting the flow of electricity. This prevents dangerous voltage buildup on metal parts of electrical equipment, reducing the risk of electric shock. Grounding electrode systems, GECs, and bonding jumpers work together to create a low-impedance path for fault currents. The grounding electrode, typically a ground rod, ground plate, or metal water pipe, is connected to the grounding busbar in the electrical panel. From there, the grounding electrode conductor runs to the grounding electrode. Bonding jumpers connect metal enclosures, such as conduit and equipment cabinets, to the grounding system, ensuring that all metal parts are at the same potential. The size of the grounding electrode conductor is determined by the size of the service entrance conductors as specified in NEC Table 250.66. The grounding electrode conductor must be large enough to safely carry the maximum fault current that could occur. For example, if the service entrance conductors are 2/0 American wire gauge copper, the grounding electrode conductor must be at least 6 American wire gauge copper. Ground rods are a common type of grounding electrode. When using ground rods, NEC 250.53 A2 requires that at least 2 ground rods be installed and be at least 8 feet in length and spaced at least 6 feet apart. The purpose of using 2 ground rods is to lower the overall resistance to ground. Metal water pipes can also be used as grounding electrodes. If a metal water pipe is used, it must be in direct contact with the earth for at least 10 feet. Additionally, a metal water pipe must be supplemented by another grounding electrode, such as a ground rod or ground plate. This is because plastic pipes or insulated couplings can interrupt the conductivity of the water pipe. Concrete encased electrodes, often called UFA-grounds, are another effective grounding electrode. These consist of at least 20 feet of bare copper conductor encased in concrete. UFA grounds provide a very low resistance path to ground. The grounding electrode system should be tested periodically to ensure that it is functioning properly. The resistance to ground should be measured using a ground resistance tester. The NEC recommends a resistance to ground of 25 ohms or less. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. Bonding is another critical aspect of grounding. Bonding ensures that all metal parts of the electrical system are at the same electrical potential. This prevents dangerous voltage differences that could cause electric shock. Bonding jumpers are used to connect metal enclosures, such as conduit, equipment cabinets, and metal water pipes, to the grounding system. The size of bonding jumpers is determined by NEC Table 250.102. C1. The bonding jumper must be large enough to safely carry the maximum fault current that could occur. Equipment grounding conductors, or EGs, are used to connect the metal enclosures of electrical equipment to the grounding system. The equipment grounding conductor provides a path for fault currents to flow back to the source, tripping a circuit breaker or fuse and interrupting the flow of electricity. The size of the equipment grounding conductor is determined by NEC Table 250.122. The equipment grounding conductor must be large enough to safely carry the maximum fault current that could occur. Ground fault circuit interrupters, or GFCIs, are an important safety device that protects against electric shock. GFCIs monitor the current flowing in the circuit and quickly interrupt the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path, such as through a person's body. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, or RFCIs, are another important safety device that protects against fires. RFCIs monitor the circuit for arc faults, which are dangerous electrical discharges that can cause fires. RFCIs are required in many areas of the home, such as bedrooms and living rooms. Surge protective devices, or SPDs, protect electrical equipment from voltage surges. Voltage surges can be caused by lightning, utility switching, or other electrical disturbances. SPD divert the surge current to ground, preventing damage to sensitive electronic equipment. Proper grounding and bonding are essential for electrical safety. By providing a low impedance path for fault currents, grounding and bonding help to prevent electric shock and fires. It is important to follow the NEC and local building codes when installing and maintaining electrical systems. Always consult with a qualified electrician if you have any questions about grounding and bonding. Understanding the NEC requirements for grounding electrode systems, grounding electrode conductors, bonding, equipment grounding conductors, ground fault circuit interrupters, arc fault circuit interrupters, and surge protective devices is crucial for ensuring electrical safety in residential, commercial, and industrial settings. By adhering to these standards, we can minimize the risks associated with electrical faults and protect people and property from harm. The grounding electrode system connects the electrical system to the earth. This connection provides a low impedance path for fault currents to flow back to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrode conductor connects the grounding electrode to the grounding busbar in the electrical panel. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. Bonding connects all metal parts of the electrical system together. This ensures that all metal parts are at the same electrical potential, preventing dangerous voltage differences that could cause electric shock. Bonding jumpers are used to connect metal enclosures, such as conduit and equipment cabinets, to the grounding system. Equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. The equipment grounding conductor provides a path for fault currents to flow back to the source, tripping a circuit breaker or fuse and interrupting the flow of electricity. Ground fault circuit interrupters protect against electric shock. GFCIs monitor the current flowing in the circuit and quickly interrupt the power if a ground fault is detected. Arc fault circuit interrupters protect against fires. RFCIs monitor the circuit for arc faults, which are dangerous electrical discharges that can cause fires. Surge protective devices protect electrical equipment from voltage surges. Voltage surges can be caused by lightning, utility switching, or other electrical disturbances. SPD divert the surge current to ground, preventing damage to sensitive electronic equipment. Always consult with a qualified electrician if you have any questions about grounding and bonding. Furthermore, it is essential to understand that local amendments to the NEC may exist. Check with your local jurisdiction for any specific requirements beyond the NEC. Thorough understanding of the relevant codes and regulations is paramount for ensuring a safe and compliant electrical installation. Remember that electrical work can be dangerous, and it's always best to consult with a licensed electrician if you're unsure about any aspect of the installation. The grounding electrode conductor should be continuous and without splices or joints. unless made by irreversible compression connectors listed for the purpose or by the exothermic welding process. The connection of the grounding electrode conductor to the grounding electrode should be made using listed connectors or by exothermic welding. The grounding electrode conductor should be protected from physical damage where exposed. When using a metal water pipe as a grounding electrode, it is essential to bond around any insulated couplings or sections of non-conductive pipe. This ensures the continuity of the grounding path. The supplemental grounding electrode, when required for a metal water pipe electrode, should be located as close as practicable to the water pipe. Grounding electrodes should be free from non-conductive coatings such as paint or enamel. The surface of the electrode should be clean and free from corrosion. The location of grounding electrodes should be accessible for inspection and testing. The grounding electrode system should be designed to minimize the risk of corrosion. Dissimilar metal should be avoided in the grounding electrode system. Aluminum grounding electrode conductors should not be used in direct contact with concrete or earth. The resistance of the grounding electrode system should be tested periodically to ensure that it is within acceptable limits. The NEC recommends a resistance to ground of 25 ohms or less. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. The grounding electrode system should be inspected periodically for signs of damage or corrosion. Any damaged or corroded components should be replaced immediately. The grounding electrode system should be maintained in accordance with the manufacturer's instructions. Proper grounding and bonding are essential for electrical safety. By providing a low impedance path for fault currents, grounding and bonding help to prevent electric shock and fires. The selection and installation of grounding and bonding components should be performed by qualified personnel. It is crucial to use only listed and labeled components in the grounding and bonding system. Never compromise in the quality or safety of grounding and bonding components. The grounding and bonding system should be designed to accommodate future expansion or modifications of the electrical system. The grounding and bonding system should be documented thoroughly, including drawings and specifications. The documentation should be readily available for inspection and maintenance. Proper training and education are essential for ensuring the safe and effective installation and maintenance of grounding and bonding systems. Always follow safe work practices when working on or near electrical equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. To energize electrical equipment before working on it. Verify that electrical equipment is de-energized using a voltage tester. Lockout and tagout procedures should be followed to prevent accidental re-energization of electrical equipment. Be aware of the potential hazards associated with electrical work. If you are not qualified to perform electrical work, do not attempt it. Call a qualified electrician. The National Electrical Code is a comprehensive set of standards for electrical safety. The NEC is updated every 3 years. It is important to stay up to date with the latest version of the NEC. Local building codes may have additional requirements beyond the NEC. Check with your local jurisdiction for any specific requirement. Understanding and following the NEC and local building codes is essential for ensuring electrical safety.